Okay, hello students, welcome back to my YouTube channel. In this video, I'm going to explain some questions that came under principle of mathematical induction. As you all know, in the combined mathematics 1 paper, you will encounter a question in principle of mathematical induction as the first question, right? So, if you are a repeat student or if you are even a fresh A-level student who are going to write your examination in 2026. Now you have just started learning the prerequisites of combined mathematics. You might have started algebra, right? So even if you are a fresh student, right, you can watch this video and no prerequisites are needed for understanding the first question, right? So I hope my audio and video will be clear to you. I'm recording this video via Zoom and will upload on YouTube. You can watch it and try to understand the questions. Okay. Now, before I start the session, I want to tell you that if you are a fresh student, you might buy your past papers after 1 year. But once you have attended the first class, it is your responsibility to buy a past paper so that you can get an idea of how questions are asked by just skimming through the questions, right? Even though you don't understand anything, you can just read how the questions are asked. Okay, you have to make yourself familiar with the questions. So by reading the past papers only, you can come to know what exactly you have to study, right? So I'm going to explain the first question now. Now, let's say you don't have any idea, you know nothing in mathematics. Doesn't matter. I will explain you one by one, step by step, like I'm explaining to a small kid, right? Okay. Now you have studied O level. You should have some knowledge. With that knowledge, you can understand the questions, right? Okay. Now, here you can see I have, okay, I'm just displaying, okay. I'm just showing the question. Okay. This is the past paper that I used while I was doing my second shy examination, right? So you can see the first question, using the principle of mathematical induction, prove that for all n belongs to Z plus, right? So we have just read the question. Now we have to extract the information from the question. Now, principle of mathematical induction means we will be given a result. Now, we have to show that the result is true for n is equal to all n. The result is true for all n belongs to Z plus. So let me write the question list here. They have given this result, right? Summation. Now, I think I have already explained the question that came in 2019 in my previous video, right? So you can just watch that video. Now I'm going to start from the 2018 because I don't want to spend much time or I don't want to waste time. So I have already uploaded some videos in which I have explained the selected question of 2019 annual past paper. So in a particular video, I explained this question also. So let me start from the 2018 A-level question. Right? Okay. Now I will just show the question now. Okay. As you can read, using the principle of mathematical induction, prove that this is true for all n belongs to Z plus. So I'm just going to first write the result that they have given. Now summation R is equal to 1 to n R is equal to 1 by 4 n square n plus 1 whole square for all n belongs to Z plus. Now, our objective is to show that the result given is true for all n is equal to n belongs to Z plus, all positive integers. Now, what we have to do is, now, Z plus means it should contain 1, 2, 3, 4, and so on, right? 1, 2, 3, 4, up to n. Okay, up to infinity. Now we have to take each and every element substitute in this equation and show that the result is satisfied. But that is not practically possible because we have infinite number of z plus, right? In the set of z plus, we have infinity number of elements. So we cannot take each and every element and substitute in the equation and show that the result is true. So for that, we have developed a concept called principle of mathematical induction, where we show that the result is true for n is equal to 1, and then we will assume that the result is true for n is equal to p belongs to z plus, right? So first step, now this is the procedure. Now procedure, first when we will show the result is true for n is equal to 1. Now we will take n is equal to 1 and we will put this condition in the equation and we'll say that the result is true. Now then we will assume that the result is true for n is equal to p belongs to z plus. Then we will show that the result is true for n is equal to p plus 1 as well. And ultimately, under conclusion, we will write, we have assumed that the result is true for n is equal to p. Then we have shown that the result is true for n is equal to p plus 1. And we have already proved that the result is true for n is equal to 1. So, according to principle of mathematical induction, the result is true for all n belongs to z plus. So, this is the procedure. Now, I will explain this question how to do. Okay. Now, let me erase this. Now, you see, we have been given a summation. Summation means, now I have to understand the concept. Summation means addition, right? So this symbol represents addition of a series. Now we have a series and the common format of this series is R cube. So I can write this as, now if I expand this is how it will appear. Now this is a series, the common format is R cube and we are adding this common format from 1 to n, which means we have n elements. We have n number of elements starting from 1. So 1, 2, 3, 4 like that, right? So in R, now R starting from 1, 2, 3 up to n. And the common format is R cube. Now this means now we have to take each and every term, right? So if R is equal to 1 cube plus summation means addition, right? Plus 2 cube plus 3 cube up to n cube, right? So this is the meaning of this summation symbol. Now, if we add this series, this will be equal to this equation. This is what we have to show, right? Now, I have to consider n is equal to 1. Now, if n is equal to 1, you see, wherever I have n, I have to put 1, right? So I will put, now I will take LHS, right? So this is left hand side. Now I'm going to take this left hand side. That is equal to summation R is equal to 1 to, here instead of n, I have to put 1. I have to put 1 R cube. That is equal to, you see, R 1 to 1 means we are going to add only this. So that will be equal to 1 cube, that is equal to 1, right? Now we will take RHS. RHS equal to this. Now here, instead of n, we have to substitute n is equal to 1. So 1 by 4, 1 square, 1 plus 1 holding square. Okay. So this will give me here 1 square, 2 square, 4 divided by 4 also will give me 1. So I have shown that the result is true for n is equal to 1. So this is the first step. Now I have to consider or I have to assume that the result given is true for n is equal to p belongs to z plus. Now we will say p is somewhere here. Now I'm going to write this way, right? So the first step is done. So I'm going to erase this, right? Okay. Now I will erase this also. Okay, this is also not needed. Just erasing to create some space to write on. Okay. Now assume n is equal to p, p belongs to z plus. We have to write this condition. We are taking an element from positive integers, which is z plus, right? Okay. Now, wherever I have n, I have to put p, right? So summation r is equal to 1 to p, r cube is equal to 1 by 4, p square, e plus 1 whole square. Okay. Now I have already explained you the meaning of this, right? This means starting from 1, 2, 3 up to p. We have 1, 2, 3 up to p number of elements, right? So this series is added p times, right? So this will be equal to 1 cube plus 2 cube plus 3 cube up to plus p cube, right? Now I have just assumed that the result is true for n is equal to p. Now my next step is to show that the result is true for n is equal to p plus 1 as well, right? Okay. Now you see here. Now this is the meaning of this. This is the meaning of this. Now what I have to do is, for showing that the result is true for p plus 1, which is the next term, I have to just add the next term, right? P plus 1 whole this cube. Now this is the next term, right? So 1 cube, 2 cube, p 3 cube. Now I'm just adding a number with the previous number. So if the last term is p cube, then the next term will be p plus 1 whole the cube. Okay, right. Now you see, I have to just write it down like this, right? Now I have just add this next term in the previously assumed result. That means summation r is equal to 1 to p r cube. Now this is equal to this that I have marked in a rectangle, red color rectangle shape, right? Plus, I'm just going to add this portion. P plus 1 whole the cube will be equal to. Now, with this result, I'm just adding this one. Now, this is a equation. Now, if we add a portion in the left hand side, the same value should be added in the right hand side also. Now 1 by 4 p square into p plus 1 whole square plus, again I have to add this p plus 1. Let me use a different text so that you can distinguish what I'm doing, right? So p plus 1 whole cube plus p plus 1 whole the. Hope the letters are clear to you. Okay. Right. Now again you see, if I consider this, now this means the series is added. The series is added and the number of terms is equal to p plus 1. So this can be written as summation r cube, r is equal to 1 and the last term is p plus 1 term, right? So this can be again written as summation r is equal to 1 to p plus 1 r cube is equal to. Now my objective is, wherever I have n, I should have p plus 1 because I have to show that the result is true for p plus 1 as well. Now you see, I'm just going to take p plus 1 square out because the p plus 1 square is common for both the terms. So half is here, p plus 1 square I'm taking out, and here the remaining is p square plus p plus, now okay, I'm sorry. Now I'm just taking p plus 1. Okay, because half 1/4 is not common in both, right? So I'm just taking this p plus 1 square and here also p plus 1 square. P plus 1 whole square is equal to 1/4 p square plus p plus 1. Now I'm going to multiply the equation by 4 and the denominator is going to be brought forward, right? So 1/4 p plus 1 whole square into p square plus 4p plus 4. Now again this can be written as 1/4 p plus 1 whole square p plus 2 whole square. Now you see, now if I write in this way, 1/4 p plus 1 whole square p plus 1 plus 1 whole square. Now wherever I have n, I have p plus 1, right? So wherever I have n, I have p plus 1. So we have proved that the result is true for n plus 1 also. Now we have a methodology for writing the answer. Now we have to first write let n is equal to 1 and let us RHS. Then we have to show that the result is true for n is equal to 1. Then we have to consider that assume n is equal to 2. After this, what we have to write is when the result is true for n is equal to p. Now you can see the writing methodology in the answer scheme also, but I have just explained the concept, right? Okay. When the result is true for n is equal to p, we have proved that the result is true for n is equal to p plus 1 as well. But we have already proven that the result is true for n is equal to 1 as well. So according to the principle of mathematical induction, the result is true for all n belongs to z plus. So this is what we have to write. Now this is very simple. If you write in this way, you can get complete marks. And even if you are a fresh A-level student, after doing this question, you might get some confidence. Okay, I also can do a question in the final paper. So you can study with enthusiasm, right? So just relying solely on the teacher's notes will not work when you study A-level. You have to work hard and you have to work smart, right? Instead of working hard, smart work should be there, right? So by attempting some past papers by yourself, and even if you attend any second year, third year, second year classes, you can come to know. Even if you are a new student to A level, you can attempt you can attend the like past paper classes, and you have to work hard, right? Nowadays, everybody is talking about Fahma Fahim, who wrote the exam 1 year earlier, right? She has done it. So you also can do it. If you are ordinary student, okay, according to your capacity, you can decide whether you can manage things, right? So I will explain the question, but you didn't need any prerequisites, only the simplification, right? We have just taken the common factor out. Okay, right. Now I hope you have understood the first question, and we will move to the 2017 A-level paper, right? Okay, 2017 A-level paper. Now we have done the 2018 and I have explained the 2019 A-level paper in my video. I will just send the link of that particular video in the description. You can watch that. I think I explained the first 5 questions of 2019 A-level paper. Now I have decided to put videos like question wise. First question, second question, like that. Okay. Now, 2017 A-level paper says, now that is also the same, right? Using the principle of mathematical induction, prove that now they have given a result. Okay, let me first write down that summation R is equal to 1 to n, R 3R plus 1 is equal to n plus 1 whole square for all n belongs to z plus. Now, this is very simple, right? So here you see, first we have to show that the result is true for n is equal to 1. When n is equal to 1, then you will just consider this series and instead of r, you will put 1. So LHS is equal to 1 into 3 times 1 plus 1. Actually, the meaning of this summation is this. If you don't understand, I will just write down this. Now, this means now we have terms, n number of terms starting from 1. So, if I put 1 in the common term, now 1 into 3 times 1 plus 1 plus, now this plus is due to this summation symbol. 2 into 3 times 2 plus 1 up to n into 3 times n plus 1, right? So this is the meaning of this summation, right? Okay. Now we will consider the RHS. Now RHS is equal to, you see, 1 into 1 plus 1 holding scale. This is equal to 4, I think. Now this is also equal to 4. So the result is true for n is equal to 1. Now when we have to consider n is equal to p belongs to z plus. Now you see, summation r is equal to 1 to p. Wherever I have n, I will substitute with p, right? So summation now you see r into 3r plus 1. Instead of n, I will put p, right? So p into p plus 1 holding scale. Okay. Right. Now you see, we have just assumed this. Now from this assumption, we have to show that the result is true for n is equal to p plus 1 also. Right. Now this means as I have written here, instead of n, we have p, right? So the next term will be this p plus, now if it is p, right? So the next term will be p plus 1 into 3 into p plus 1 plus 1, right? So this will be equal to p plus 1 into 3p plus 3 plus 1 means 3p plus 4. 3p plus 4, right? Now, with this, I have to add that next term. With this, I have to add that next term. So this will be equal to summation r is equal to 1 to p. R into 3r plus 1 is equal to p into p plus 1 holding scale. Now the next term after pth term will be added with this assumption, which means p plus 1 plus 3p plus 4. P plus 1, 3p plus 4 is equal to plus p plus 1, 3p plus 4. Right. Now, you see, if I consider the whole series, that will be equal to summation of r is equal to 1 into p plus 1 because the final term is p plus 1th term, right? So this can be written as summation of r is equal to 1 to p plus 1, right? R into 3r plus 1 is equal to, you see, now we have to simplify this, and wherever I have p, and I have to get p plus 1. So if I now this is what I have to obtain, right? So p plus 1 holding scale. Now no, p plus 2, right? Because p plus 1 plus 1 of p plus 2 holding scale. If I get this, now we are done, right? So let's try to simplify this, right? So I can take p plus 1 out because in both terms we have p plus 1 in common. So p plus 1 is taken out. So we will have p into p plus 1 plus 3p plus 4. Now p plus 1, p square plus p plus 3p plus 4. Now this is equal to p plus 1, p square plus 4p plus 4. Now, if you simplify, definitely you will get this. Now we are done. So ultimately, you have to write. We have assumed that the result is true for n is equal to p, and we have obtained the result is true for p plus 1 as well. And we have already found that the result is true for n is equal to 1. So according to the principle of mathematical induction, the result is true for all n belongs to Z class. Right? Now we have done 3 questions so far, and we will move to the 2016 A-level paper also. Right? 2016 is also the same, right? So you see, the questions are replicated. Can you see this? Summation r into r plus 1. Here we have r into 3r plus 1, but here we have r into r plus 1. And here we have an expression, but that is actually different from the expression given in the, the before question, right? So that was held in 2016. Now, after this question has come. So when you compare this expression, this is a bit easy, right? Okay. So I hope you can do this, and we will look at the next question also. 2015. Right. Now, this is a bit different. 2015 question is a bit different. Now we will try to answer that question. So my purpose is to make you confident, right? So even without studying the prerequisites, unwanted algebraic things, you can try the past papers, and you can just study what are actually needed, and then I think after 10 minutes, the meeting will be ended. Okay, anyhow, I will try my best to complete the question within 10 minutes, right? Okay. So the question says I think. Okay. So I'm just showing the question to you. I don't know if you can clearly read or not. Using the principle of mathematical induction, prove that 8n minus 3n is an integral multiple of 5 for all n belongs to Z plus. So this is the question, right? So we have a function of n is equal to 8n minus 3n. Now we have to show that this is an integral multiple of 5. So integral multiple of 5 means what? Integral multiple of 5. So this is actually fifth multiplication table. 1 times 5 is equal to 5. 1 times 5, 2 times 5 is equal to 10. 3 times 5 is equal to 15. Likewise, we have, right? So integral, these are integers. Multiple of 5 means this is the product and these are factors. Now this is a multiple of 5, right? This is this 5, this 10, this 15 are multiple of 5. And these are integral multiple, means they are exactly multiplied by 5. Now, this is also the same procedure. First, we have to show that the result is true for n is equal to 1. Then we have to show that the result is true. Now we have to assume that the result is true for n is equal to p. Then you have to show that the result is true for n is equal to p plus 1. Now, f1, if n is equal to 1, f1 is equal to 8 1 minus 3 1. Okay. Now this will be equal to 5. So 5 is an integral multiple of 5. So that is true. Now we will consider that when if p is equal to integral multiple of 5. Now we are just considering this, right? So 8p minus 3p. Now we have to show that. Which means, see, now you see, if you consider 5, if you write 5 as a multiple of 2 numbers, in the multiple of 2 numbers, 5 is one number. That is the meaning of integral multiple. Now again, if you split this function into 2 factors, one number will be 5 and 5 into something. So this is equal to 5 into something, right? This is what we are considering. Now again, we have to show that for p plus 1 is also, this is true. Now if I substitute, if p plus 1 is equal to 8p plus 1 minus 3p plus 1. Right? Now, you have known, right? So, under indices, you might have studied. If the bases are same, you will just add the exponents. For example, a power m into when they are multiplied. A power n is equal to a power n plus n. Now, if we have m plus n, I can write in this way. Now, I'm going to just use the vice versa of indices theorem. Now, this will be equal to 8p times 8 minus 3p times 3. Now, you see, 8, the bases are same. We have to just add the exponents. Here also the bases are same. Then you have to add the exponents. So you see 1, here also 1, p plus 1, p plus 1. Okay. Right. Now you see, now I should have 5, right? I should have 5 because I have to make relationship between 5 and this expression. So this 8 can be written as 8 power p into 5 plus 3, right? 5 plus 3 minus 3p times 3, right? Now, again, I'm just going to expand, right? So, now this can be written as 5 times 8p plus 3 times 8p minus 3p times 3. Now, you see 5, 8, p plus, now 3 is common here. Now I'm going to take this 3 out, right? 8p minus 3p. Now you see, in this expression, we have 5. And here also we have 5. For example, if I have 13, now 13 gets written as 10 plus 3. Now, in this 10, we have 5. 5 into 2. But this 3 cannot be written in terms of the multiplication of 5. So this is not an integral multiple of 5. But 20, if we have 20, this can be written as 5 plus 15. Now, both numbers that are used to obtain this number 20, which is an integral multiple of 5, by adding, we can tell, I hope you can understand my idea, right? So this 20 is an integral multiple of 5. Now I have split this into addition, 5 and 15. Then the both numbers are again integral multiple of 5. So here we have 5. Here also we have 5 because we have already written this as 5 into something. So 5 into something plus 5 into something. Definitely I can take this 5 out and this plus this. So for p plus 1 is also the expression or the function is an integral multiple of 5, right? So this is how you have to write the answer. And since we are running out of time, it's time to wind up the session. And I will meet you in another video explaining the second structured essay questions that came in the latest past papers as the second question, right? Okay. Bye.